Let's have a big hand for Mark Isaacson.
All right, so we're going to talk about how you can reuse code by leveraging the C++ type system. And to prepare you for kind of the level of this talk, I should say that we're going to start off very easy, and we're going to build up to code that I don't think anyone in the room has seen anything like. So just be prepared for that contrast, where the beginning is going to seem almost too easy. It's going to be things that I expect everyone in the room to know. And the reason why I'm starting with basics is because I want to change the way that you think about them. I want to reframe how you think about techniques that you may already know, both the easy ones, like templates, which we'll see in a couple slides, but also kind of when we get toward the end, we're going to get into things like curiously recurring template pattern, and I'm going to show what I think is an atypical use of that as well. So be prepared for that. But the roadmap going forward is as follows. We're going to talk about how you can reuse an implementation. So I've got multiple types. I want to do approximately the same thing. How do I make that work? We're going to talk about how I can select implementations. So I have the same function. I call it with multiple types, and I do the same semantic operation in two different ways. And the example that we'll use is a case for optimization. So we'll talk about how you can use techniques like tag dispatch to say, I would like a fast path and a slow path of the same algorithm. And the last thing we're going to talk about is opt-in functions and mix-ins. So I have a type, a widget, let's say, and I would like my widget to have a power, to be able to do something that it wasn't able to do before. And who's responsible for giving it that power? How do you give it that power? And to do that, we'll dive into even a little bit of C++20. So starting from humble beginnings, 2 calls to max, one with ints, one with strings. What I think is very exciting about these 2 lines here is that I call a function, I give it 2 different types, and it just works. It knows that as long as you can compare things with less than, you can give me the maximum. You can tell me which one is bigger than the other. Now, for some of you, maybe that doesn't seem all that impressive, all that nice. It's very simple. But think back, if you will, to C, where if you're trying to do the absolute value of something, if you're trying to get the absolute value of some numbers, if you're talking integers, that's abs, and if you're talking floats, it's fabs. And I don't know about you, I tend to think that programmers have very little cache space, very little space to remember all these little nuanced, kind of nasty names. So if I want to write a function that just works with all types, does roughly the same thing, a template is the answer. If you want to share an implementation, think templates. That's what templates are. They're sharing. And we said that the requirement to be able to call this function is having a less than operator. And so in C++20, you'll be able to hopefully have concepts and therefore write the following code. We say it is less than comparable. That is the requirement of T. If it is not the case, you'll get a lovely compiler error message. So hopefully simple review. I want to spend some time talking about a function called getNthElement that we're going to write together. And not to be confused with std::nthElement. If you know that, this isn't it. GetNthElement, you give it a container and it gives you the thing at position n, at index n. So I have a list of int, I have a vector of int, I call getNthElement, and in both cases it produces the correct answer. Now, there's a catch to this. I could write this as a single templated function. And if I did that, it would work for both containers. It would produce the correct answer for both containers. The downside is the performance for vector would probably not be what we want in the naive solution. Vector can do this operation in constant time, in O of 1 time. List cannot. List must go through all of the different elements and produce it the long way. And so how do we make it so that getNthElement works for both types, but is fast for vector? Does anyone have an idea for what technique we might want to use? Yes, in the front. So the suggestion is we can see if the container has O of 1 access. And you're getting ahead of me. That's a great insight, though, and we're going to talk about that in a bit. Yes? Template specialization is a suggestion, and I believe that, yes, you can do it with that. But we're going to start even more simple. I believe I just heard it, and that is overloading. So for starters, we need a version of the function that works with list. So I have a function, it takes list of int, and it does it with a loop. This is the slow way. It's the only way, though, for list. We get an iterator to the beginning, we walk that iterator n times, we dereference it, and that's the answer. And for vector, I have a version of the function, and we call subscript because it's just dirt simple. And the nice thing about vector, and this is an idea we're going to come back to, is that a vector is basically implemented as a pointer to some data, an array of data, and a length. And because we can do arbitrary arithmetic on a pointer, we can go from the front to the nth element as a constant time operation. So fundamentally, that is the reason why vector can be fast. Take these two bodies, put them next to each other. This is overloading. And all of a sudden, my example from before for vector and list just works. It works for both types of containers, and it works as fast as it possibly, can for both types of containers. All right. Now we have a dec of int and a vector of double. And those bottom two lines don't compile. And that's kind of unfortunate, because I would like to be able to use any container with getNth element. And I would also like it to be fast. I would like, my vector cases to be fast. And I could add some overloads. I could overload on all four of these container types. That sucks. This talk is about code reuse. So obviously, any time that we're copy pasting code, we're losing. It's a common bit of advice to follow. If you're copy pasting code, stop what you're doing, rethink. Overloading is not what we want to do here. But that vector of double case can probably use the same code as the vector of int case, and that should remind you of templates. So let's generalize. Here's a version of the function getNth element, and it works with any container that you give it. It will accept any container, and it will produce the correct answer. But I actually spoke about this before. If we just have this is pretty unsatisfactory. It will work with all the types. For vector, it will be too slow. It won't, it will not be efficient. Overloading to the rescue. Again, getNth element, it accepts any vector, this time templated over whatever you want to put inside. So we can mix overloading and templating to get sharing between implementations. Any kind of vector will use that second function, but also generality. Now you might wonder at this point, what if I call getNth element with a vector of int? Won't it match both of those overloads? Wouldn't that be an error? And the answer is no. The reason it's not an error is because even though both would compile, the second one is more precise. That is another idea that we will come back to. All right. Something is still not quite right. I have a fast path and a slow path, and my list will use the slow path. My vector of int, my vector of double will both use the fast path. What don't we like about this current solution for getNth element?
It's out of boundary.
Oh, it's out of bounds for the last one. Yes. Wow. No one's ever pointed that out before. Good job. You're paying attention. I like that in an audience. So the A case is just awful, but assume that I had written 1, 2, 3, 4, 5 again. Thank you. I appreciate that. I will edit the slides. Yes. So yeah, I believe the observation was that it is slow for dec. And dec also supports a constant time version of getNth element. I could write an overload that is constant time for getNth element. And again, I don't want to do that because that would be copy pasting. So things are about to get harder. So quick review, if you want to share an implementation, that's templates. If you want to distinguish between implementations, that's overloading. If you need both, just use both. So our goal now is to make getNth element accept all containers, standard containers, boost containers, the containers that you've written in your code bases, all of them. And furthermore, our goal is to make it so that if an O of 1 solution is supported by that container, we do it. We always do the fastest thing we can. That is our goal. So I want to talk about what the requirement is to be able to do that. So I have a list of standard containers here. We know that vector supports the fast path. We know that dec supports the fast path. List does not. What is the rule that says, yes, I can do the faster version? Ideas? Yeah, so the idea is random access iterators. And before I go into that, I want to talk about a bad heuristic. So a less good heuristic, you might be wondering, hey, we used subscripting before. Can't I just use subscripting to be able to do this? The answer is no, and the reason is things like map. If I had a map of integers, Subscript doesn't mean get the thing at position n, it means get the thing with key n. So the correct observation from the audience is the real power we need, the real power of a container that says, yes, I can do this in constant time, is to have a random access iterator. So here is our generalized constant time solution. We get an iterator to the front, we advance it by n times. This goes back to our vector example from earlier, where we just said, hey, it's basically a pointer, so we can just add to it. And then we dereference and get the result out. Our O of n solution stays exactly the same. Doesn't have to change at all, it accepts any container. There's a problem, though. If I put these back to back, if I try and make them overloads, and I call getEnthElement with a vector of int, this is now ambiguous. And the reason it's ambiguous is because vector of int could compile for either version of this function if you had it on its own, if you were not overloading. And the templates are equally precise, and because they are equally precise, that is a compiler error. The compiler does not know that for vector we should use the bottom one. And so what we're going to talk about next is how do we tell it which version to use. And for that I need to get abstract on you. So for the next few slides, if you've not seen this kind of thing before, I don't expect it will make a lot of sense right away. It's going to build up to a complicated result. And so bear with me, it'll all come together. So there's different kinds of iterators. For those of you that don't know, iterators follow kind of an inheritance hierarchy of powers. We start at the bottom with input iterators. They support exactly 3 operations. One is equality. Are we at the end yet? You can dereference. You can say, get me the current element, and you can iterate. You can go forward and say, look at the next one. Those are the 3 things it can do. Bidirectional iterators do all of that and can go backwards. Random access iterators can do arbitrary arithmetic. Basically anything you can do to a pointer, you can do to a random access iterator. So why does this matter? We have these types in the standard library, these standard iterator tag types, and they're empty. They don't contain any data members whatsoever, but they inherit each other the same way that the iterator concepts do. These tags also inherit that same way. And if I have a set of overloads, a foo function overload at the bottom there, with one with a forward iterator tag and one with a random access iterator tag, and I call that with a forward iterator tag, an instance of forward iterator tag, that's the curly braces, am I going to get the first or second overload? Shout it out. The first or the second overload with the forward iterator tag instance? The first one. And the reason I'm going to get the first one is because it is a precise match, right? Forward iterator tag is going to go to the forward iterator tag overload. How about when I call it with a bidirectional iterator tag? It's the first one. So the reason it's the first one is that a bidirectional iterator tag is a forward iterator tag because of inheritance. And for the last one, for the random access iterator tag, I get the second overload. And that is a little bit more complicated because a random access iterator tag is a forward iterator tag, but the second overload is more precise. So both work. The second one's more precise. That's the one that would get chosen. Why does this matter? Well, if I go back to my constant time implementation and I add a third argument, the reason we couldn't use overloading before is because we had 2 arguments in both versions of the function. Both the constant time and the O of n time one had 2 arguments, and they were exactly the same, and so the type system couldn't say, choose this overload or that one. So we're going to add a third argument, and that's the one that we will be overloading on. The first 2 are exactly the same. The third argument, its only purpose is overload resolution. And to highlight that, I didn't even give it a name, because I don't care about the value. In fact, it's empty. It has no value. All it is a type. Now, the other thing that I changed in this slide is I've called this function getEnthElement impl. This is an implementation detail. And one thing that you'll see in a second is that this ultimately is hidden from all of your users. And that is a wonderful property that is not shared by other techniques that let you do this, like enable if. But otherwise, exactly the same. We do the same thing with the O of n implementation. We add a tag type at the end corresponding to the capabilities of the iterator we need. And here's the magic. So I have a function getEnthElement. It takes any container, and it forwards to getEnthElement impl. And the trick is, those first 2 arguments are still the same. We never touched them. But we're adding a third one, that tag. And the magic in the middle, what that does is it says, for whatever container you passed in, give me the tag of the iterator that corresponds to that container. So if you give me a vector, it will give you a random access iterator tag instance. And if you give me a list, it will give me a forward iterator tag instance. And I can pass that to getEnthElementImpl. That is then what lets overloading happen and then lets me select between implementations. So I can either go to the fast path or the slow path. Now the magic in the middle. Let's talk about that. So for starters, there's this thing in the standard library, standard iterator traits, and you pass it an iterator type, and out from it you can get a bunch of different things. One of those is the tag type. And the curly braces at the end there, all they do is instantiate one of them. The key idea here, the key idea behind tag dispatch is that you can take any condition that you want and map, it's a compile time map operation from the set of all types, the set of all container types, onto a fixed size, smaller set of types. In this case, all of those tag types we were talking about. And because that's a fixed size, it's maybe 5 different types, I can overload on that. Instead of having to overload on all types that I know about and all the types I don't know about, all of the containers that you've written in your, homebrew libraries, I can just overload on the tag types. That's the idea behind tag dispatch. It is a generalization of overloading that makes this all work. So confused, no problem. Here's a quick example of tag dispatch as it shows up in your standard library. Hold on, I'll show you it in just 1 second. Copy n is a function in the standard library, and what it does is you give it an input range, say an iterator on a vector, the number of things you'd like to copy, and a destination to copy it all to. That's all it does, and the most simple implementation that you could have is a loop that goes through and just uses the copy constructor to copy from the source to the destination. That's the easy way. But in all of the standard library implementations that I've looked at, I know that GCC does this, Clang does this, Visual Studio does this, there's an optimization. And perhaps some of you have thought to do this in the past. And instead of using copy n, maybe you said, I know that memcopy and memmove are faster. If I'm using ints, if I'm using simple types, I can just take the bits and move them from one place to another. And if you did that, you're doing stuff that your standard library implementer has already done for you. If you call copy n, it does tag dispatch to get to these 2 implementations. For things that it can support, it uses memmove, and for things that don't support memmove, it does the loop that we know works with every single type that you possibly can, calls the copy constructor, so on and so forth. Now you might be wondering what those true type and false type things are. I'll get to that in just a second. But first I want to talk about why this optimization exists. To understand why this is better, I need to talk about memmove and how it works under the hood. So memmove says, I have a bunch of bits. Not I have a bunch of types, I have a void start to a bunch of bits. And I want to copy some number of bits from one place to another. And it does that bit for bit, whatever it happens to be. And if that's integers, that's great, because an integer is just a bit representation of a number. But if it's a string, strings are more complicated. An easy implementation of a string might be a pointer to some data and a length. And if I called memmove on a string, I have the original now with the pointer pointing at the data, and I have a copy with another pointer that is bit for bit the same as the original, pointing at that same data. We never call the copy constructor. Both of these think they own the data. When they destruct, both of them will try and free the data, and you have a bug. So for some types, you cannot do the fast thing. But for integers, it's way faster than the loop. So how do we select between one version or the other? There's a type trait in the standard library, is trivially copyable, right? Can we just take the bits from one place and put them in another? Is it the same? And if you can, you just use that extra true type or false type that comes out from that to say, use the first version, use the fast version, or use the slow version. So tag dispatch is a wonderful technique, and it's great for optimizing things and hiding complexity from your users. Now, suppose I just wanted to benchmark the impact of tag dispatch as a technique. Suppose I didn't do a fast path. Just both of them have the same implementation. They both do the loop. They're both the slow version, no matter what type you gave to it. Is there a runtime overhead from using tag dispatch, from just forwarding to these two implementations as opposed to our original copy n with the loop right there in line. Is this any worse? What do people think? If you think that it does have a runtime impact, raise a hand. I see a few. So how about people who think it does not have a runtime impact? How about people who think it's equally efficient? People who aren't sure or don't want to say. Awesome. So it turns out there is no runtime overhead. That is only true, however, if you have any level of optimization turned on. You need to have enough optimization to get inlining, which I believe turns on with O of 1. So if you can inline, what's going to happen is, for starters, the tag type, it knows that you never use it. So dead code elimination in the optimizer immediately just kills the tag type. It uses it for overload resolution, but otherwise you don't even get an instance of it. Then you might wonder, okay, well, I'm calling another function that I wasn't calling before. But these are templates, and the compiler is great at inlining. So when you call copy_n with an int, it says, okay, well, only one of these implementations is ever used with an int. That's the top one. So grab the loop, grab the body of the function, put it into copy_n when you substitute an int, and just use that. And the same thing is true of strings. So everything gets inlined, everything gets dead code eliminated, and it's as efficient as if you just written it as a partial template specialization. Which is good news, because it's just a free performance win. There's no cost to doing this at runtime, and the compile time cost is very minimal. So what's the high-level idea behind tag dispatch? We generalize overloading. We map the set of all types onto the set of a small set of types that we can overload on. It lets us disambiguate cases that would otherwise be ambiguous. And we can use all the different type traits that are given to us by the standard library to do this. We can dispatch on, is it polymorphic? Is it the same type as a different type? But it's even more awesome than that. There's another type trait called std::conditional. And you can give that any compile time Boolean expression. So if you can write a constexpr function that returns a bool, you can plug it into std::conditional, and when it's true, you'll get one type, and when it's false, you'll get a different type. So any condition you want, you can select between different implementations. So if you can use the type system to say, this is a good one, this is a bad one, you can use this technique. Now, why do we like it? Where's the value? Well, we abstracted a concept, getEnthElement, and it works with everything that supports that concept. We didn't say this works for some things and not other things. It's not just our pure overloading solution we started with. And it's as fast as it can possibly be for anything that you can possibly give it. Things that are available to you when you write the function, things that exist only when you link it with some other library. Anything you want. And all of your users never have to know how you did it, why you did it. They can just trust your code is fast. And the last thing is that it composes. Again, users don't have to know anything. Print nth_element is as fast as it possibly can be. It accepts all containers, and getEnthElement hides all of that complexity inside of it. Now, for those of you that know your standard library very, very well, you might have realized that I could have used a piece of the standard library that already did all that tag dispatching to implement getEnthElement. Does anyone know what I'm talking about? How I could have, I see a hand off in the corner, maybe shout it out. std advance. So there it is. This is a better solution. std advance, you give it an iterator, you say walk it n times. I can get the iterator out and dereference it. And this is better because it packages that complexity. It packages all of that kind of hard stuff that we've just spent a while building up to and talking about in a neat package that you can reuse in more places. The big idea here is if you have something complicated, put it into the smallest possible abstraction you can, reuse it all over the place. And turns out you can go even more simple. std::next is a one-liner. So we're going to change gears a little bit. I'm going to talk about opt-in functions. And to start, we're going to have a widget. And for our example, we cannot modify widget. Widget is third-party code. And whoever the author was, they decided they wanted to implement equality, but not inequality. And so the question is, how can we make that bottom line compile? How can the user of the code say, I would like widget to have the power to use inequality on it without being able to change the source code of widget itself? Implement a free function, yes. So I can do a free function, and in fact, that's what I'm going to do. So I namespace my function for a couple reasons. One is it's just kind of nice, because otherwise if you don't namespace it, then everything in scope automatically would get not equal. But if I write this free function, I can write not equals in terms of equals. And you can imagine the standard library actually does this with std::relops. If you have a class that has a less than operator and you pull the relops namespace in, you get greater than, you get greater than or equal to, you get less than or equal to, you get not equals and all of the different operations just by having implemented less than. But in our case, I can't fit that on a slide, so equal to not equal. Cool thing here. This line says, bring that power into scope. A widget only has the power of not equal when the namespace is available. I think that's kind of interesting. I think that's an unusual use of namespaces. Most of you use namespaces to say, I don't want to violate the one definition rule and clobber somebody else's class. This is, I would like a power to become available. I think that's interesting. Using statements, by the way, can be done at both function and class scope. Very useful in header files. But this makes our example compile. And again, anything in the scope of foo would suddenly now have a not equals operator. But let's say I can modify gadget. Gadget is source code that is not third party. I can change the implementation. I would like to give it a not equals from the equals equals operator it already has. And again, in Boost, there's a version of this that's very similar to relops. You would implement less than, and it would give you all of the other operations. And I think that's more compelling than this example, for which you could just as easily write the one-line not equals operation in line. But inheritance is a great way to get more powers. And what's more is inheritance can also give you data members, it can give you new methods, it can give you all kinds of other things. So this technique is generalizable beyond just comparisons. But our goal is to make that bottom line compile with the magic of inheritance. And to do that, I want to talk about something called CRTP, Curiously Recurring Template Pattern. And if you've not seen this before, that's just a fancy way of saying gadget inherits from not equal mixin templated over gadget. The base class is templated over the derived class. That's the technique that we're going to use. And here's where things get interesting. So ignore the middle for a second. The bottom line is the one that we're familiar with. That's the one that says, we've got these things that have equality on them, negate it, there's the answer. Everything up to that is just magic. The first line, where we give the function signature, we will accept anything that is a not equal mixin. And gadget inherits from not equal mixin, so it is a not equal mixin. Anything else is not in the club. Anyone else can't use this function. So inheritance with CRTP is a great way to say, only these people can call this function. Now, if we ignore the static assertion for just a second, and we go down, I have a couple static casts. And what those do is they say, go from the base class, the not equal mixin, to the derived class. So in this case, we go from not equal mixin of gadget to just gadget. And importantly, there are references all around. The references are important because otherwise we might slice off the information of the gadget. So we convert our not equal mixin to the derived class, the gadget class. We can then, because it is a gadget, and we know gadget has equality, negate that operation. The top part, the function signature, is only there to say, this type is allowed to call this function. And the static assertion just verifies that you're not misbehaving. It is for malicious people. It is for attackers. It checks the invariant that, yes, not equal mixin templated over derived is the base class of derived. If you could call not equal mixin with, or the not equal operator with not equal mixin templated over int. You are physically capable of doing that. But if you do, you'll be caught by the static assertion. So that's the only reason why that's there. Now, this version of bestowing a power, this version of saying only these types are allowed to call this function, is something that we're going to come back to, and I'll reference as we talk about more advanced opt-in techniques. So just hold on to this. It's going to show up again. Suppose I wanted some of my gadgets to be able to use not equal and others not to. And by the way, if you're thinking for a second, why would you ever want to do that? I agree. Let me give you an example where sometimes you would like something to have a power, and sometimes you would not want it to have that power. Imagine, if you will, a world in which shared pointer, you could say some of the time I want the ref count to be atomic, and some of the time I don't want it to be atomic, because I can reason about the program and safely say this shared pointer is only ever used by a single thread. Well, if you wanted to be able to do that, that would be an awesome thing, to be able to give your users the power to choose. I want the one with the atomic version or the non-atomic version. And so that, we're going to talk about how you would allow that in terms of talking about equality and inequality. So just an example, but that's a better reason why you might want to do this. Does anyone else have an example of a power that you might want to have for some of your instances, but not all of your instances? Maybe something that has a performance cost. No? Well, maybe instrumentation. Maybe you want to instrument some instances and not others. Let's look at how we would do this. So, ignoring the templates for just a second, we have the same equality, we have the same integer, and at the bottom I've got just a couple of type defs, a couple of using aliases that say gadget is shorthand for gadget input with no template arguments, and we have the not equal version as well. And then the templates are kind of interesting. This is variadic CRTP, the same thing we were just talking about, but you can give any number of mixins and it will just work. So what does this look like to the compiler when it stamps it out? Well, if you call this with no template arguments, there's no inheritance. So it's just a gadget. It's the same original gadget that we were talking about before. But if you do have a template argument, again, we inherit from not equal mixin of gadget impl templated over not equal mixin. So it's the same thing. This is what it would look like if you were to write it all out. But there it is. I think that this kind of sucks. The reason it sucks is because, unlike the tag dispatch we talked about earlier, we can't just hide that away in std::advance and reuse it over and over and over again. Somebody, if you want to be able to do this kind of thing, like me, has to know complicated, terrible template magic and CRTP and do these kind of static assert, static cast things to make this all work. This uses the same non-member version that I showed you a few slides ago. We can package it up in C++20. We can make this so that it is as easy to use as a shared pointer is. You don't need to know any of the complicated magic that makes it happen. You can just say, I would like to add a power to this class, please. And in fact, you can do this with a class that you're not allowed to change. So imagine, if you will, a widget that, again, only supports equality, only has some powers, and I would like to add a power to it for some instances, but not others. And I cannot change widget itself. In C++20, I can write this mixer class, which says, behave exactly like a widget, but add these powers to it. Add this mixin on top of that. And the thing that lets us do that in C++20, if it gets in, no promises, is something called operator dot. So this is what this is going to look like. I'm going to hide some of the template magic for just a second and talk about operator dot and what it does. So if my only requirement right now is I want mixer to behave exactly like a widget, I have that code on the right, mixer of widget m, and I can just use x, the data member inside of widget, and that just works. And operator dot is what allows that. So I have operator dot. What it does is it takes the data member I've stored inside, my widget that I've stored inside, and says return that by reference. Now, how does that fit in? Well, operator dot's a lot like operator arrow. Operator arrow is the thing that makes unique pointer and shared pointer work. It says, if you're using this type in a context of dereferencing, so if you're calling arrow on it, if you're calling dereference on it, keep dereferencing until you can no longer do so, and then whatever method or member you were using, use that on the result. Operator dot, very similar. When I try and access the data member x there, it says, does mixer have a method or a member called x? If yes, use that. If not, call operator dot and try using the method or member on that instead. And it recursively does that until it can no longer, call operator dot and give you a compiler error. So this mixer right here behaves exactly the same way as a widget. That is the power that C++20 gives us. Now add to that the CRTP we had from before. We take a mixin, we do our inheritance with templating the base class with the derived class. And all of a sudden, this mixer behaves like a widget and is a not equal mixin. And the same not equal function I showed with the static assert and the static casts works with this mixer. I think that that's pretty cool. And of course, if you want to make it variadic, you can make it variadic. So this is pretty magical. Hopefully we're going to get this. There are some more compelling reasons why we might want operator dot, but I thought that this was pretty nifty. So what have we been talking about? We talked about how if you want to do roughly the same thing with multiple different types, think templates. If you want to distinguish between implementations, if you want to be able to do different things, a fast path and a slow path, if you've got an optimization, that's a great time to pull out overloading. And if overloading turns out to be ambiguous, or if you need something more complicated to say which version you would like to select, tag dispatch lets you map the set of all types into a set of smaller types that you can then overload. And you can use any condition you want to do that. No more are the days where you need to remember how to do a slow thing and a fast thing. Just do one thing and have it understand under the hood how to do it best. We talked about opt-in functions. We talked about using namespaces for something atypical to bring a power into scope. We talked about how designers can use inheritance to add powers without adding any data members. It doesn't even feel like a traditional interface, let's say from another language like Java. What it is it's saying, I am this not equal mixin. Therefore, I can call these functions. But I could add data members, and I could add methods. And if I wanted to be able to do so for some instances and not others, C++20 might offer us a good way to do that. And with that, I'm Mark Isaacson. Thanks for listening, and you can find this and other talks on my blog.
Mark, thanks very much. And obviously, questions now, please. We've got a reasonable amount of time, so please raise your hand.
So can you access private members with this operator dot?
So the question is, can you access private members with the operator dot? And the answer is no. The only reason why I was able to access the private member in this case is not because of the private or publicness of that value type, but because operator dot returns that is why I'm able to access it. So if X inside of widget was private, I would not be able to touch widget. Because X is public in widget, when I return a widget reference from operator dot in mixer, I'm able to use the public methods, the public members of that. Hopefully that makes sense.
Then you cannot override any behavior of your class, right? You just can operate on the public interface.
So the question is, can I override the behavior? And the observation is I can only operate on the public interface. And that is correct. I cannot do traditional inheritance with operator dot. It is not the same as inheritance. Interestingly, though, here we do have both inheritance and operator dot. So in this case, the powers from the mixin actually have priority. Because when operator dot asks, can you perform that operation on mixer? If the base classes, if any of the base classes have that member, have that method, it will use that version because it is the mixer is that type. And it is only if that fails that you'll then be able to call operator dot. So if I did put a function with the same name in mixer, or if I had a data member X inside of mixer, it would prefer that one and use that one without ever calling operator dot.
What is the biggest advantage of these techniques against enable if and template specialization?
So the question is, what's the advantage of these particular techniques over partial template specialization? So I actually wrote about that quite a bit on my blog, so you can find a very detailed answer there. Tag dispatch has some different trade-offs. So I really like tag dispatch because you can hide all of the complexity from your users very easily. It's built in. In fact, you can't forget it. So you have an interface function, and then you forward to the complicated, crummy details that have the extra type on the end that your users probably don't want to know about. With partial template specialization, that's often a little bit more difficult because it's easier for them to see that you've done that. Also, template specialization often uses things like enable if, which kind of clutter up the interface, so I don't like that so much. But the thing about tag dispatch is that it only works for functions. So you can use tag dispatch anytime you've got a function, and I think it's the best way to kind of do this selection process if you've got a function. If you've got a type like a class, if you've got a struct and you need two versions of, let's say, the deleter for unique pointer is a great example, then that you can't use tag dispatch for. You have to use the pattern matching built into partial template specialization, and so that would be an appropriate place to do that instead.
I have a question because you said that there's no overhead, but I don't remember any kind of ensuring that there's really no overhead. Do you know any way to make sure that there's no overhead other than looking at the assembly code?
Yeah, so again, I actually went into this in my blog, and I did look at the assembly code. So take those functions, plug them in on godbolt.org, or I think it's gcc.godbolt.org, which lets you enter in a random C++ program, and it will show you the assembly with some color coding. And if you do that with tag dispatch and you go to different implementations that are actually just the same, it will show you that if you have any optimizations turned on, it just completely gets rid of all of that, inlines everything, dead code eliminates the tag type, and has no runtime overhead whatsoever.
All right then, let's wrap it up, shall we? And have a big one for Mark Isaacson.